Thank you very much. Actually, it's really not the first time, and I'm very excited to be here again, and I'm excited that Tolia Vershik is here. I tell you why. Because he invited me for the first time, and at that time, which was like, I don't remember, there was a feeling that there is a kind of collapsing of the mathematics in St. Petersburg. You know, there was people were leaving, and Vershik was the one who was stood up. He stayed here, insisting to revive the mathematics in St. Petersburg and keep it as a great place as it used to be for so many years in the history. And it's such a pleasant to come here and see that you really succeeded. It's really working so well. So well, I mean, I really remember that at that time there were a lot of people who were looking for jobs outside, and now you attract people not only to come back, but even people who are not from here who are coming. It's really wonderful. So it's a real pleasure to be here once again and to see so many people. And I want to talk about kind of a very, very general talk about high-dimensional expanders to give. Let me start with ordinary expanders, but very, very briefly, this subject got a lot of attention, so I guess most people do know something about that, but still, let me give a very brief history. So, what are expanders? Let X, VE be a finite graph, so V is the set of vertices, E is the set of edges, and the Chigger constant of the graph is the minimum of this value. What is it? This is, you go over all proper subsets of V, and you look how many edges are going from W to its complement, and you divide it by the size of W if it's the smaller than the complement, or by the size of the complement. And you take the minimum over all size. What does it really mean? It really means that the Chigger constant is small if the graph looks like that, right? And then you can kind of cut it into two pieces. Very little is going from one side to another. Those people who are familiar with the Riemannian geometric notion of Chigger constant, that's basically the Chigger constant from Riemannian geometry, or the kind of isoparametric invariant. And we say that the graph is, that the graph is epsilon expander if h of x, it should be capital X here, is at least epsilon. And a random, so you can kind of imagine why this notion is very important in computer science, because you really want to get graphs which are very much connected. You see, if you have a graph like that, it's connected formally, but it's not really connected. You can come here, cut few edges, and make it disconnected. When you construct, for example, when you construct networks, you want the graph to be k-regular with k. Well, I'm saying graph, but I always really, we are not engineers, we are mathematicians. So I'm talking really about an infinite family of graphs, which are all k-regular with the same k. Usually you want k to be as small as possible, and you want epsilon to be as large as possible. So you want to get a sequence of graphs which you don't pay much for the number of edges, but you still want it to be very connected. And these are called expanders. If you think about it for a minute, it's not at all clear that expanders exist. The first to prove it, well, there is an historical dispute here, which I don't want to get into it, but it's usually attributed to Pinsker that random k-regular graphs are expanders. This is proved by the kind of Erdos type of methods that you take a random one and you prove that it's expander, but it's non-trivial somehow to check if a given graph is epsilon expander, because you have to go over all subsets, right, which is an exponential number. Margulis was the first one to get an explicit construction, and he, in the following way, he said if gamma is generated by a finite set S, and assume it has the Kazhdan property T. If you know what is it, fine. If you don't know, this is a fancy type of property which many discrete groups, especially arithmetic groups, especially lattices in simple Lie groups, are known to have. And then you look at the Cayley graphs of gamma mod n with respect to S, where n runs over the normal finite index subgroups of gamma, you get an infinite family of Cayley graph. All of them are K-regular with the same K because we are using the same S. Formally, we use the projection of S to gamma mod n. We get a family of K-regular graphs, and they all epsilon expander with the same epsilon, which this epsilon related to the epsilon in the Kazhdan property. I don't want to get into that. I just want to say that this, by nowadays, standard, the results of Margulis is an easy observation, but this open a world of connections between the theory of graphs and representation theory, a kind of infinite dimensional representation theory, and it led later on. Well, there was some work on the connection between expander and the spectral gap. The spectral gap, we mean the following. We look at the matrix A, the adjacency matrix of the graph. So if the graph is with n vertices, with say K, let's say K regular graph on n vertices, it's not difficult to see that, well, because the graph is, the matrix is symmetric, all the eigenvalues are real, it's not difficult to see that all the eigenvalues are between K and minus K. K is always an eigenvalue. If you multiply it by the vector 1, 1, 1, 1, 1, you just sum up the rows, and because there are K neighbors, you get K as an eigenvalue. Minus K is an eigenvalue if and only if the graph is bipartite. Anyway, you can check whether X is an epsilon expander if lambda 1 is bounded away from K by some epsilon prime. And epsilon prime related to X, and X is related to epsilon prime. I'm a little bit vague here. So, but the real meaning of it, that if you want to get expanders, what you really want is to bound the second largest eigenvalue from the largest one, which is K. A well-known proposition of Halom-Bopanna is that you can never do better lambda 1 if you take an infinite family of graphs. Lambda 1 will be always at least, approximate 2 square root of K minus 1. So let's define a graph to be Ramanujan. Well, the name of Ramanujan associated here with some reason that I don't have time to fully explain, but let's call graph Ramanujan if all the non-trivial eigenvalues are indeed bounded by these 2k square root k minus 1. So in this sense, Ramanujan graphs are the optimal expander from this spectral point of view. And this connection that Margulis initiated between representation theory and the combinatorics of finite graphs led later on in the 80s to the construction of Ramanujan graphs, and in the following way. Let me just give you the building block of this graph without really explaining how and why. Well, you take F to be a local field. You know, the kind of things that Prasad talked about in his first talk today, like if the p-adic number, or if you prefer a local field in characteristic P, you take PGL2F divided by a compact maximal subgroup. If you will take PGL2R and you divide it by a maximal compact subgroup, you will get the upper half plane. If you do it over the p-adics, you get a tree. That's the Boatitz tree. This is the symmetric space in the case of p-adic Lie groups. If you then come up with some discrete group gamma I is a congruent subgroup of some arithmetic group gamma. If you know what it is, fine. If you don't know, maybe even better, because you shouldn't confuse yourself. What is important for us, that if I have a discrete co-compact subgroup of PGL2F, then you see I divide on one side, I divide by K, I'm getting a tree. On the other side, I divide by an action of a discrete group, so I'm getting a tree divided by a group. So I'm getting a graph, but not just a graph. The graph is compact because we assume that this is a co-compact subgroup of it. So I'm getting a compact graph, namely a finite graph. So this is kind of a fancy way just to present specific finite graph. And then some work of Margulis and some work of Philip Sarnak and me, and then my student Morgenstern and other, somehow using fancy theory of Deligne and Drinfeld from the theory of automorphic forms, prove that this way you get Ramanujan graph. So this is kind of a not so easy theory, but this is already done in the 80s to get Ramanujan graphs. And now there is a long history about expander and Ramanujan graphs, as I said before, random graphs by Pinsker, Kashdam property T by Margulis, Ramanujan graphs by these automorphic forms. There have been some more elementary method which gave expander by some computer scientists. Recently, by the theory of interlacing polynomials, you got Ramanujan graphs, not explicit one, but existence. Anyway, there is a long and very interesting and beautiful theory, but this is not the topic of my talk. Those who want to read about that are invited to go to there is an excellent survey of Khoury, Linia, and Wigderson about the application of expander graphs in computer science, and maybe not as good survey by me on the application of development of the last 15 years, that suddenly expander, which really started by the computer scientists, and for many years the pure mathematicians were helping the computer scientists by providing them Ramanujan graph and expander. Suddenly it appears in number theory, in geometry. There is a nice history, and you can find, you meet expanders so often these days. If you go to Google and you write expanders, you will get 4 million mention of expanders, but before you are getting excited, you will see that 95% of these are a type of expander. So we should be a little bit more modest and see our importance in the world. When we say that expanders are all over the places, they are not as important as this type of expander for humanity. Anyway, I want for a second, if I may allow, I'm not sure, I hope it won't, I will not regret. I want to show you one of the application of expander to computer science. It's one of my favorite, but I really do it because my talk is about I-dimensional expanders, and I will show you some using the theory of error-correcting codes why we kind of anticipate a real difference between one-dimensional expander and I-dimensional expander. I want to stress the message of my talk is, you know, when you say I-dimensional expander, maybe some people get a feeling, okay, for 40, 50 years, a one-dimensional theory has been developed. You know, the people are sick and tired. They have to look for some jobs for their students, so they say, okay, let's study I-dimensional expander. The main message of my talk, that it's not just generalization for the sake of generalization, but there is really a new phenomena which will come into the game, and which with potential even down to earth applications. So let me say a few words about codes, and just I will try to watch the time that it doesn't take doesn't take too long. An NKD code, that's religiously somehow the computer scientists, they always use these letters, N, K, and D code. What is it? Is just a subspace of F2 to the X, where X is really N, the size of X is N. So this is called the length of the code. K is the dimension of the code. So the code is nothing more than a subspace I'm talking, say, about a linear code. That doesn't. You can talk about non-linear, but it doesn't matter. So a code is a subspace of F2 to the N of dimension K. I mean, of course, you want to think about it that you have a map from F2 to the K, which is your information, the bit that you have information of length K, and you send, instead of sending a bit of length K, you send a vector of length K, you send along the channel a vector of length N, and the extra bits are supposed to teach the receiver how to correct mistakes if something was corrupted along the channel. And now D is the minimum distance of the code. To start with, the minimum distance, you mean you take the distance between alpha and beta, the minimum distance over all alpha and beta in the code. But if the code is a linear group, in the linear subspace, you can take alpha, is really the distance of alpha minus beta from 0, which is the Hamming weight of alpha minus beta, which is also in the space. So the distance of the linear code is simply the minimum Hamming weight of the vector in the code. Ideally, what do you want? You want, so everyone understand that an ideal code, an ideal error correcting code will be that N is not too large with respect to K, and D is as large as possible. The rate of the code is K over N, the normalized distance is D over N, as the term good code, going back to Shannon, who initiated this theory in the 40s, that codes, or a sequence of codes, more precisely, again, we are mathematicians, right? Not engineers, is a family of code with the rate and the distance are both bounded away from 0. Now, there is another term which let me introduce. A code, if you have a code which is a linear subspace, you can take C-perp. What is C-perp? These are all the vectors in F to the N which are orthogonal to the code. Orthogonal mod 2, right? We take the inner product, like between the two, it equals 0. You can think of every such W as a linear functional defining the code, right? Now, in C, we don't want to have vectors with small support, right? That's exactly the issue of the distance of a code. On the other hand, in the dual, we do want to see vector with small support because we want to define the code by equations which are as small with small support. Because think about it in a practical life. You send a long vector whose size is 10,000, right? And you want to check whether it's a legitimate word. You prefer that the checking whether it's a legitimate code word will be a very quick computation. So you want that C-perp will be spanned, will be spanned by set of vectors of bounded degree. If this happens, again, when n goes to infinity, we say that this is low density parity check, LDPC, this going back to Gallagher. And Gallagher, who invented the notion in the 50s, but not too many people pay attention to him. Only it took like 30 years then that it became an extremely important. Nowadays, even in industry, LDPC is a notion that they are using all the time. And the first people who made explicit construction So again, Gallagher proved, you see, let me give you in 30 seconds the history of error correcting codes. Shannon invented the notions, proved that there exists good codes by saying I will take random linear functionals and I will take their set of solutions, and these are good codes. And then people work to get explicit construction. Gallagher came and said, even if you will take random equation with bounded support, it still works, you still get good code. But to find explicit construction turns out to be much more difficult, and this was solved in the late 90s by Sipser and Spielman. When Spielman got the Nevalina Prize a few years ago, the committee praised this achievement as one of his three major contributions, even though it's a very undergraduate class. Actually, it's a beautiful application of combinatorics and linear algebra. So maybe let me tell you very quickly the construction of Sipser and Spielman. He started with a graph VE, k-regular graph, let's say on M vertices, and E the edges will be n times k over 2, right? If it's a k-regular graph. Now, in a second, we will see that our code will be functions on the edges. So this will be our n, m times k over 2. Actually, the k here is a sin, because I should keep k for the dimension of the code. It's not. K here is the k regular, is the degree of the graph. Okay? Now, Sipser-Spielman said the following: let B. So we are going to have a family of k-regular graphs, which are going to be very good expanders, in fact, kind of Manujan graphs. And they said, let B be a fixed subset of F2 to the k. K is going to be fixed. So this is, we'll call it a small code, but it's fixed for us. And then they define, now for the family of graphs, all of them are k-regular. They define the big code to be CXB. These are all functions on the edges. Functions on the edges. Some that for every vertex in V, for every vertex in V, the vertex V looks around. When he looks around, he sees K edges. So he really sees a vector in F2 to the K. You put some order on them, it doesn't matter which one. So he sees its local view is a vector in F2 to the K. So you want that this vector is inside the small code. Okay? This is their construction, and then they prove, it's a very elementary, they really proved that the rate of C is at least twice the rate of B minus 1, and the amazing thing is that the delta, the normalized distance of the big code is, you can relate it to the normalized distance of the code and lambda 1. You remember this lambda 1 of the graph. It's kind of an interesting combination of the properties of the small code and properties of the big eigenvalues of the big graphs.
What does this mean? Move to the ground the vertex.
You put numbers. You put some numbering on every vertex as k edges coming out of it. Yeah. Put on them any order number you want, 1, 2, up to k. Then the function give value 0 or 1.
Arbitrary order.
Arbitrary order, and it doesn't have to have any compatible. On the same edge, you give it a number when I look from one vertex, and you can give it a different number when you look from the other side. The function to 0, 1 is defined the same. But the order doesn't matter. Anyway, you deduce from that if you have a family of expanders, and if you arrange for the code B to have rate more than half, and the delta of B the normalized rate to be more than lambda, then eigenvalue. So if you take Ramanujan, you can get this to be very small, then you get I don't want to get onto that. The proof is not difficult. I can kind of give you the feeling for the proof. The proof for the rate is completely trivial. It's 2 lines of linear algebra. The interesting part is the proof of the distance y. Assume you have a function on the edges, a 0, 1 function. What we want to prove, if it is inside the code, we want to prove that the function has very high weight, right? That it's not too many zeros. So you say, okay, well, if this is 0 function, we don't have to prove anything. But if it's a non-zero, so it's non-zero on one edge. But if it's non-zero on one edge, I know that this delta of B is at least lambda, so there is more edges around that vertex which are non-zero, and more edges around the other vectors for which the function will get non-zero. And then you continue like that, you continue like that. The expansion property of the graph shows that eventually you have a linear amount of non-zero elements. You have to prove something, but it's conceptually, it's not a difficult proof. Okay, it will come up again at the very end of the talk. So let me jump to the I-dimensional expander. What is I-dimensional expander? The I-dimensional theory deals with other simplicial complexes or with hypergraphs. Basically, simplicial complexes and hypergraph, at least the interesting one, are exactly the same thing. The distinction is that if you are a computer scientist, you talk about hypergraph. If you are a mathematician, you talk about simplicial complexes. Because I'm going to talk either on D+1 uniform hypergraph. What does it mean? We have a V is a finite set. A D+1 uniform hypergraph is a collection of subsets of V, all of them of size D+1. So if D is equal to 1, we are getting graphs, right? If D is bigger, we are getting bigger. This is called hypergraph. Mathematicians prefer D-dimensional pure simplicial complexes. So this is a collection of subsets, faces of W, which is closed under inclusion. But to say that it's pure, you say that all maximal faces are of size D+1. So the only difference is, if you have an hypergraph, you really take also the subsets of all the subsets, right? And if you want to go for a simplicial complex to a hypergraph, you take just the maximal ones. Anyway, it's clear that, so I will speak the language of simplicial complexes, and then we can speak about edges, triangles, but just from a pure combinatorial point of view, right? A triangle is just a subset of 3 points. Okay. Now, maybe before showing that, I probably would have to ask you, what is the definition of an I-dimensional expanders? Right? We got the definition of expanders. We got actually 2 definitions. One was the original combinatorial one, which says that every subset has many edges going out of it, and there was another one about spectral gap. Now, to be honest, there are many equivalent conditions on a family of graphs to be expander. And each one of them, you can start to guess what is the I-dimensional analog of it. But to be honest, we don't know which definition is the better one. Unfortunately, if we start with different definitions which are all equivalent to each other, if you guess what is the I-dimensional analog of it, suddenly they are not necessarily equivalent. In fact, part of the current research is sometimes to check if they are equivalent or not. But it's even worse. In a way, even the same property you can extend to I-dimension in several different ways, which sometimes are equivalent, sometimes are not. So some of the research these days around I-dimensional expander is even to look for the correct definition. To be honest, probably there is no correct definition. There is probably more than one definition. Depends on the applications, etc. I will show you one or two, and you can decide for yourself which one you prefer. Anyway, surprisingly, the more difficult notion of Ramanujan complex, the Ramanujan graphs, can be extended, at least from the examples that I gave you. It's kind of clear what should be the higher dimension analog, because you remember we talked about PGL2. We talked about PGL2. You see, PGL2 divided by K divided by gamma I, right? Let's just replace PGL2 by PGL. PGL2 gave us one-dimensional. If we'll work with PGL D plus 1, it will give us D-dimensional. Here's the story. We talked before that PGL2 of a p-adic field divided by a maximal compact group give us the Boas-Titz tree. The theory of Boas-Titz is not limited just for PGL2. It's for every PGLD. In fact, for every simple Lie group over the p-adic numbers. If you take PGL D plus 1 and you divide it by a maximal compact subgroup, you get the Boas-Titz building. The Boas-Titz building is an infinite, contractible, d-dimensional simplicial complex, like the tree, right? It's a higher dimensional version of the tree. If you divide it by an action of a co-compact group, you get a finite simplicial complex. And if you do it in the same way, and if you replace the work of Deligne and Drinfeld by the work of Laforgue, you get Ramanujan complexes. Laforgue, I mean Vincent Laforgue. I hope you noticed that everyone who worked for us got the Fields Medal. Deligne, Drinfeld, Laforgue. Laforgue got the Fields Medal exactly for that. He didn't prove that. What?
That's the brother.
No, Vincent, the brother. Laurent, sorry. Yeah, you're right, Laurent. No, Vincent will come also here. The two brothers will come in this talk. Wait, sorry, I am confused. Laurent got the Fields Medal exactly. Well, he proved the Langland's conjecture, which implies the Ramanujan conjecture. In fact, I want to be very honest with you. I started to work on that. Well, I'll be even more honest. There was a very nice student at Yale, Beth Samuel, which unfortunately passed away shortly after she finished her thesis. She studied with Piasecki Shapiro automorphic form, but she was kind of stuck and looked for a research problem. And I have a kind of a part-time position there. I come there every year. So she came to me and she asked, maybe I can suggest her a problem. I told her, I don't know what happened. I know that Laforgue proved the Ramanujan conjecture for GLD. We did a lot of mileage out of GL2 of Drinfeld. There must be some combinatorial applications to the work of Laforgue. It will be interesting to look at. Turns out to be much more difficult than I thought, and together with Uzi Vishna and Beth Samuel and myself, we developed a theory of which we call Ramanujan complexes, which basically we define what are Ramanujan complexes, and we prove that Laforgue work gives Ramanujan complexes. To be honest, of course it gives, because we define Ramanujan complexes in a way that Laforgue results will give Ramanujan complexes, right? But at that time, we didn't really have any application in mind, and that's why I wanted to show you this slide, because I'm really impressed by the government of India, who knew very early to appreciate our work, and they called the place in India Ramanujan complex because of our paper. It's even more impressive, they did it 15 years before we wrote our paper. So they really predicted there will be such an important paper called Ramanujan complexes, and that now, and for few, we wrote the paper around 2005 or 6, something like that, and nothing happened with this. Unfortunately, as I said, shortly after that, Beth Samuels had cancer and she passed away. But suddenly, the story was completely changed, and those, if I talk too fast up to now, I'm going to start a new lecture now. So even if you lost me, it's an opportunity. I'm starting a new talk, and eventually the two talks will be related to each other. The talk...
And about this topic.
What?
Connection with buildings?
The building is that you take the Boatitz building, which is an infinite object, you divide it by an action of a co-compact lattice, and you get a finite simplicial complex. This finite simplicial complex, under some condition, it's not completely general, under some conditions are what we call Ramanujan complexes. I don't want to give definition, it's fairly complicated, but for example, it gives you some spectral bound on eigenvalues of various Laplacian. There is more than one Laplacian. You know, in higher dimension manifolds, it's not just one Laplacian, you have higher Laplacian. So you can talk in this language. There are several languages that this can be said. I'm going to present it in one of the surprising applications that will come up. Eventually, the two subjects are going to connect to each other. I'm starting now a completely new talk, which connected also to Erdos in an interesting way. Erdos presented the following problem many years ago, and two young kids, Borush and Furedi, who were at that time undergraduates in Hungary, both fairly well-known computer scientists and mathematicians, but the theorem is the following: you put endpoint on the board, and you have then you draw all the possible triangles between this point. Okay, so you have n/3 triangles, right? You draw all the n/3. 2/9 of them are going to meet. There's going to be a point on the plane which is covered by 2/9 of that. And the 2/9 is, by the way, is the optimal one. That's a beautiful kind of theorem in the theory of convexity. Shortly after that, Barani proved the higher dimensional version of it, which says the following: fix D greater or equal to, there exists some constant C of D, for D equal to, it's 2/9, some constant bigger than 0, such that if you take P to be any subset of the Euclidean space R to the D of n points, then we are going to take the n choose D plus 1 simplices, which we can draw on those n points. There exists a point which is covered by at least this positive proportion of the D simplices determined by D.
CD is known?
What? CD is not known. It's a famous open problem. It's not even known how it's not difficult to see that it goes to 0, but it's not known how fast it goes to 0. There are some interesting problem, which is it's still an open problem. Let me before I will give you the amazing theorem of Gromov related to that. Gromov came and completely changed the point of view on this type of theorems, and he proved amazing results. But I want to give a definition which is essentially due to Gromov, but I will speak in a slightly different language and I'll to relate it to expander. So let's see. Let X be a d-dimensional simplicial complex. We say that X has the geometric epsilon overlapping properties. In a minute, we'll define also the topological overlapping properties. There are two different properties. If for every map from x0 means the vertices of the simplicial complex, right? For every map, if you take a map from RD, then for every affine, well, if we are talking about affine, there is a unique. If I have a simplicial complex and I take a map from the simplicial complex to R to the D, once I say to you where the points are going, everything is uniquely determined, right? Because the edge between them must go to the straight line between them, etc., right? So I say for every, because the topological story, that's the second, for every affine extension, there exists a point Z in R to the D, which is covered by epsilon fraction of the images of XD. XD, this is the set of D simplices. So what is Barani theorem? Barani theorem really tells us that if you look at the complete D-dimensional complex, you take n vertices. In order to define a simplicial complex, I have to define you what are the subsets. Take the subsets of size at most D plus 1. This gives me the complete D-dimensional simplicial complex on n vertices. Barani theorems tell you that when n go to infinity, right, they all have the same epsilon overlapping property. Now let's read it again with the topological. Gromov tell you that they also have the topological overlapping property, namely, not only you take any map from the vertices, but then you extend it in any way you want continuously, not necessarily affinely, they still have this property. This is Gromov results. They still have the CD property. In fact, Gromov proof is much stronger results with a constant CD, which was better than what was known before for the affine case. Just to illustrate to you how amazing is this theorem, let me show you a short movie.
What is that delta?
What is what?
Delta.
Delta n. Delta nd is the complete d-dimensional simplicial complex on n vertices. So you take n points, n going to infinity, you take all the subsets of size at most d plus 1. Okay? Even the case d equal 2 is really amazing theorem. Let me show you the little movie. Oh, no, what? Oh, just a second. No, let me, no. What happened? I'll go back to this. It should work here. You have to do it.
This
No, I think, well, at least, okay, do this. I don't know. Well, let's see if it works. No, I think I at least I'm supposed to do it right from there. Yeah, look at this little movie. Okay, I mean, it's not so easy to do with many points. So of course, if you do it just with 8 points or so, I can cheat you, of course. But believe me that I. No? So you see, first of all, this is the Barani theorem, the Boruch-Furedi theorem. You take 8 points, you take all the possible triangle between them, and what you will see that eventually there is some area, which is little area. Well, in this case, not so little because it's only 8 points, which is covered by many of them, at least 2/9 of them. Okay, So this is an illustration. Now this is actually, it's kind of expand, but it's exactly the same location of points. But now, by the meaning of the theorem of Gromov, that you allow to do your triangles in any way you want. In particular, I can make the triangles very, very narrow. And I can avoid completely the area of intersection in the Borosh-Foredi theorem. I can arrange now, if this gave me this area as the Borosh-Foredi, I can arrange now that I have to do this triangle. I will do it like that. I will avoid it completely. I will avoid it completely. I will make them very, very narrow. I will this with this, and this I will do with this. So I'm allowed to do whatever I want. Just to be careful, once you picked up, and then the theorem of Gromov tell you, it won't help you. You will get, with the same 2/9, you will get another area which will give you this, even though it's completely different one. You try to escape from it, but it will catch you over there. Okay? It's kind of an amazing theorem of Gromov, because if you, can we get back to, it's kind of amazing when you read it for the first time, you think that it's really impossible, and between us, Gromov is not always so careful about his writing, so when I read it for the first time, I thought that something is missing here. And even now, when I know the proof, I still find difficult to believe that this is true. Now, what all this has to do with expanders? Okay? What all this has to do with expander? Look at the case of one-dimensional. Look at the case d equal 1, and assume XVE is an epsilon expander. Let F be a map from the vertices to R to the D, R to the 1, to the real number. So you get here a map, and somehow you send your, I don't know how, you send your vertices to R. Now choose a point here, call it Z, such that half of the points are above it and half of the points are below it. Okay? So this amounts to dividing the graph into two subsets, each of them of size half of the graph, right? The property of expanders tells us that there are many edges going from one side to the other, right? So if we will make a continuous function from the graph to R by what is called the intermediate value theorem, all the edges which are going from that side to that side, when they are projected to the real number, will have to cross this point. Right? So you see that expander graphs have the epsilon overlapping property. So we allow ourselves to call, if you have a family of simplicial complexes have the epsilon overlapping property with respect to affine map, we will call them geometric expanders. If they have the stronger property, we will call them topological expanders. So this is one of the most amazing generalizations of the notion of expanders to high-dimensional case. But the surprises are coming up. So this is the definition. A family of d-dimensional simplicial complex we will call geometric expanders if they have the epsilon geometric overlapping, and topological expander if they even have the topological one. Excellent. Now, Gromov, but let's see, what we saw up to now. Up to now, the theorem of Barani and the theorem of Gromov told us that the complete complexes are geometric expander or topological expanders. Let's go back to the one-dimensional case. To prove that the complete graph is an expander is a completely triviality, right? The whole point of the theory of expanders was to prove that there exist bounded degree expanders. Right? We said first proof random, property T, Ramanujan, interlacing, whatever. The whole point is with bounded degree. So Gromov put forward the following fundamental problem. Are there bounded degree geometric or topological expanders? He asked it around 2010, and within few years he gave an answer in a joint work with Jacob Forks. Now this is Vincent Laforgue, the brother of Laurent Laforgue, Asaf Naor and Janos Pach. They prove that for every D, indeed there exists bounded degree simplicial complex. What is a bounded degree? Bounded degree means that every vertex is inside only a bounded number of cells, of simplices, right? Like in the complete one, if you take the complete one, every vertex is in something like n to the d. It says, now they give two proofs. One is random. They prove that random, they have a model of random, which I don't have time to explain, but if you think about it, you probably will guess what it is. And suddenly they took our Ramanujan complexes and show that our Ramanujan complexes have this geometrical overlapping property, namely they are geometric expanders. Okay, very nice. So, well, I have to say that I was thrilled, and then I started to study this theory and to learn. But what about topological? Topological, much, much more difficult to prove. Eventually it was also solved. What would be your guess? That Ramanujan complex, okay, first guess will fail. You would predict that random complexes, bounded degree random complexes, are topological expanders. Not true. They are not. Not that we don't know to prove. We know to prove that they are not. So you see, here is a kind of, in fact, Gromov at some point was not sure if bounded degree topological expander do exist at all. Maybe it's too strong property. Surprisingly, eventually they exist. The proof uses Ramanujan complexes, but here is another surprise, a warning. We don't know if the Ramanujan complexes themselves are topological expanders. The proof is very crazy. It's based in somehow on the original method of Gromov, who related this topological expander to some kind of an isoperimetric inequalities on the cohomology mode 2 of these simplices. So it's a long story which I'm not going to touch, very complicated one. But eventually, first of all, in the
theorem.
So the dimension we eventually proved, this is the first work was joint work of Tali Kaufman, Kashdan, and myself, and then my student Shai Evra and Tali Kaufman completed in all dimension, and the result is the following. Is very, very strange. If you take X to be a D plus 1 dimensional Ramanujan complex, which is a D dimensional, we don't know if it's topological expander. What we can prove is that it's D minus 1 skeleton. You kind of ignore the top level and you take it one dimension less. We know to prove that Dirs are topological expanders. But eventually, because we know it for every D, then it means that it solved Gromov problem for every D, but not really in the way we would love to solve it.
But there is a P.
And what?
There is a P.
Okay, the P is the p-adic number. So we have to take the degree. That was even in the work of, in the geometric. Okay, I should be honest about one more point. Bounded degree with graph, you can get the degree 3 are already expander. 4, 5, it's even easy to prove. If I tell you which numbers we have to take here as our bounded degree, you may feel that this is a joke. Our bounded degree is maybe 10 to the 1,000, or maybe 10 to the 100. So we need to go to a huge number. So we have to take prime P, very large, p-adic number, the degree to be, the building to be very thick, And then we fix it, and then we divide it by nodes. I don't have time to explain, but it's all. Okay, I still have 7 minutes. I want to go back to this story of a local testability and co-boundary expander. Okay, because this is a potential, I want to show you that this theory of I-dimensional expander is not only, it's kind of, as you can see, it took us to a new subject which never been seen before in the one-dimensional case. Nobody thought of expanders as topological expander when it was one-dimensional. It was only the imagination of Gromov which took us to this world. So you can see that suddenly they appear there. I want to show you some potential of applications in computer. Already a few applications, I will hint on some applications and even more dramatic potential applications in computer science. So let me just do it very quickly in the few minutes I still have. The notion of co-boundary expander, okay, as I hinted to you, the crucial way, the way to prove that these Ramanujan complexes are topological expander is by proving some results on their cohomology, which nowadays we call it co-boundary expanders, which I don't have time to explain. But co-boundary expander turns out, which already appear in some work which is in semi-computer science of the work of Nati Lineal and Roy Meshulam, who study random simplicial complexes. And they, basically I can say very quickly, they basically wanted to generalize the theory of Erdos and Reini of random graphs. The theory of random graph is very famous by now. It started by Erdos and Reini, and there is an industry of results on random graph. Lineal and Meshulam wanted to extend this to, say, even two-dimensional. What does it mean to be a random two-dimensional simplicial complex? So they said the following, what does it mean at all? With random graphs, you take n points, and you decide on every vertex, is it inside or outside with probability p. In the two-dimensional case, they said, I'm taking n points, this is their model, you can argue if you like it or not, but their model is the following. It's not a bounded one in our sense. But anyway, they said, I'm taking the complete graph on n vertices, and then on every triangle, I decide with probability p, which is whether it's inside or not. Okay, what type of question I want to ask? The first question that Erdos and Reini asked was, is the graph connected? What should we ask in dimension 2? Is the complex connected? Of course it's connected. We started with the full graph. They said no. Connected for graph mean that vanishing of the first cohomology group, H0. So for us, connected will be vanishing of H1. And for D-dimensional, vanishing will be, connected would mean vanishing of HD minus 1. And they prove beautiful results extending the work of Erdos and Reini about this result to this vanishing cohomology. And exactly the same property that Gromov used when he studied the cohomology of these limits appear in their work. Tali Kaufman and now showed that this is also something which has application to a subject which is maybe the most exciting subject in theoretical computer science these days, called property testing. What is property testing? Let me illustrate it by a major open problem in the theory of error correcting codes. In fact, when Sipsper and Spielman did their work, which was the thesis of Spielman, they wanted to solve this problem. They couldn't solve this problem. And they solved the LDPC problem. What is local testability? Which again, it's extremely important theoretically, but also practically. Nowadays, people are talking about codes which are very long. Let's say you send a string of length 200,000. And the receiver is getting it, and if the number of mistakes is less than 5%, he has an algorithm which can correct it. But if the number of mistake, if it's completely corrupted, like 40%, there is no chance. So locally testable code, locally testable, are codes which allow you to read only random, say 50 bits out of the 200,000, and will tell you if this is indeed a code word or at least very close to it, probabilistically. And they're very much looking for locally testable good codes, and this is a major open problem there. Now, it's known that local testability implies LDPC, but not conversely. Moreover, we are here in a situation which is a completely new paradigm in the theory of error correcting code, because over the 70 years since Shannon, the theory was always random is the best, and we are trying to get explicit construction which are as good as random. Random codes are known not to be locally testable. But high-dimensional expander are, in a way, what did I do? Yep. High-dimensional, okay, I'll say it. High-dimensional expanders have intrinsically some local testability. Here is the point, and that will be my, I have 1 minute and a half, and that will be my last sentence. If you take a graph, a very large graph, there are graphs, expander, even Ramanujan, of I-GERT, namely no small cycles, which means that if you look at it locally, you think that this is a tree, right? On the other hand, there are graphs which look like a tree locally, I-GERT, and they are very bad expanders. They are not expanders at all, which means you don't know from the local structure, you cannot deduce globally. On the other hand, the seminal work of Garland, who proved the so-called Serre conjecture about buildings, the vanishing of the cohomology of building modulo gamma, showed that if the links of high-dimensional expander for dimension at least 2, it's not true for dimension 1. If the links are very good expanders, you can deduce globally vanishing of cohomology, namely you can deduce a kind of a high-dimensional expander. Namely, you have properties of high-dimensional expander can be checked locally, while properties of graph cannot be checked, or this type of property cannot be checked locally. Nowadays, a group of us is trying to do the Sipser-Spielmann construction, instead of doing it on Ramanujan graph, to do it on Ramanujan complexes with the hope to get local testable code. And if this will succeed, then I will come for the third time to St. Petersburg to talk about that.
Thank you very much. Is there any questions?
An intermediate Laplacian play a role in this.
Yeah, you can define it in the combinatorial way. You can define so many of them.
Yes.
The amazing thing about the Ramanujan, you get them all. It's automatically in some sense. It's the kind of take your best dream that, and if it's Ramanujan, then all of them. Namely, you can define a bipartite graph, such that on one side you put all the triangles, on the other side you pull all the edges, and you take the lines between them. Then you get the optimal bound you can opt for. Because somehow you take everything to the building, and the Laforgue work is so strong that it gives you many of these. So I'm sure that there are potentially, I'm sure that these complexes are answering many questions about simplicial complexes, especially questions that have never been asked before.
For graphs, you have a very good developed spectral graph theory. And it turns out that it works with expanders very well. But for hypergraph, as far as I know, you have no good spectral theory.
So for this, that's what you better think about simplicial complexes and not about graph, which is the same object combinatorially, but take also the intermediate steps, and then you can talk about many different Laplacian. For example, take all the possibilities of 7-dimensional faces against 3-dimensional faces and make it to a bipartite graph and check that. And you can prove results. For example, what type of results you want to dream about, right? You want to say one of the properties of expanders is that if you divide your set, the set of vertices, into two pieces, there are many edges go to side. What is the dream property for a d-dimensional set? If you divide the set of vertices to d+1 subsets, you have many cells, each one has one leg in those sets, right? So you can prove all these type of results for these Ramanujan complexes. So they're really... the amazing thing about them, I mean, and that's even about expanders and about Ramanujan graph, but I think it's even more dramatic in the high-dimensional case, that at the same times, they behave like random, and at the same time, some of them have huge amount of symmetry. They are kind of Cayley complexes of finite groups. So they have a huge automorphism group, a lot of symmetries. The fact that at the same time, you have so much randomness and pseudo-randomness and so much symmetry is a kind of contradiction almost. And as you know in mathematics, if you start with contradiction, you can prove everything, right? So basically...
So maybe I will try to ask
sure.
Special question. So you use some special theory, or you use some more general theory in this case, or you just prove all the statements on Laplacians just for this case?
Basically, just for these cases, we take from the shelf the big work of Laforgue, okay, about the Lagrange. It's a deep work on Lagrange-Ramanujan type of conjecture for automorphic forms for PGLD, and we looked for them. What's the meaning of them combinatorially? Okay. And the meaning of them is exactly tell you that it behaves like a pseudo-random in many different ways. If you want, many of these Laplacian are elements of the Eka-Ivahori algebra, if you are familiar with this story, so you can kind of get there.
Yeah.
I want just to make some story. Alex started with the importance of expanders and finished. He was visiting Texas A&M University where I'm working, and I was evidence of the following. We are speaking and he gets telephone call, and it is former Prime Minister of Israel, Barak.
Barak, yeah.
Barak. And he is asking Alex about some properties of expanders. So is this true story?
Well, basically, but Barak,
Alex told me
our ex-prime minister, when he was kicked out from the job, became Iran kind of an adventure capital, you say, and it was proposed to invest money in some company which has some idea. By the way, it was a company of Dorian Goldfeld. Some of you may know him. That used cryptography. Now, he is actually a graduate of mathematics, Barak. You know, he has a first degree in mathematics from our department. And I am basically the only mathematician that he still knows. So he called me and he wanted my advice about this proposal. I told him that Goldfeld is a friend of mine, so I should better ask somebody else.
Yeah, and I'm doing my message. Remind me to tell what to tell.
I told that
Alex was a member of Knesset, and by the way, because of this, I lost $2,000.
What?
Because he invited me to Knesset to show Knesset when there was a procedure of awarding Sarah and bought by Wolf prize. And I was flying from Minneapolis, and I was suggested $2,000 just not to escape the flight.
Oh,
The plane was full, but I wanted to see Knesset, and I wanted to get that procedure, and Alex was my guide at first. Okay.
I started to be panicked that you really lost $2,000.
Okay, any more reminiscence or questions about venture funds or other things? Okay, if not, let's thank Alex.